Hello, I am Grigore Roșu. I'm the founder and CEO of PySquared. And our mission at PySquared is to bring all programming languages and the next million of developers to Web3. It is well accepted and broadly acknowledged and proved over and over again in surveys that fragmentation is one of the main critical pain points in Web3. Fragmentation of ecosystems, blockchains, providing different languages, different applications, fighting with each other for the users, to steal users from each other. Liquidity, billions of dollars spread all over, and the user experience is terrible. Everybody wants to fix it. Let me tell you how we want to approach, how to solve this problem of fragmentation. Through universality. Universality at three different levels. First, universality in programming languages and program execution. We firmly believe that all programming languages should be available to Web3 developers. Universality with respect to verifiability and proof mechanism. Verifiability should not be negotiable. Every execution should be provably verifiable. And we should also allow different proof mechanisms. We should not be stuck with just some of them. Also, universality with respect to distributed consensus protocols that assure security. We should be able to achieve consensus at the speed of light for applications that operate that way. How precisely we do that? So we offer a universality stack containing three components: the Universal Language Machine, the Universal Settlement Layer, and the Universal Consensus Protocol. The Universal Language Machine is a blockchain architecture that allows you to write smart contracts in any programming language, existing programming languages or new programming languages, even in programming languages that have not been invented yet. You can even bring your own language, BYOL. Plug and play your language into the blockchain and then write smart contracts in the language. ULM builds on top of the USL, the Universal Settlement Layer, which allows you to generate proofs of execution for any programming languages, executions with any programs in any programming languages, therefore proofs also across different ecosystems based on different languages. And also it is fast and low latency settlement. And when we talk about proofs in this presentation, we mean two types of proofs, both mathematical proofs and zero-knowledge proofs. Usually, in the blockchain space, we understand zero-knowledge proofs by proofs, but you'll see that mathematical proofs are even more important when it gets to actual correctness. And the USL, to achieve all these performance benefits, builds on top of the Universal Consensus Protocol, which is a consensus protocol for claims that are true, and it is not based on or relies on a total order of transactions. It is a set consensus protocol. You achieve consensus on a set of truths. And this can be done, amazingly, at the speed of light. Literally, all you need is a round-trip message between the client and the verifier to get confirmation that this claim is true and to achieve agreement on that. All right, so what does this really mean? Well, it means the following, that through ULM, we can now bring all the developers in the world to Web3. They can use their favorite programming languages. They no longer have to learn obscure programming languages in order to be part of the Web3 space. That includes millions of developers out there, tens of millions of developers, not to count all the AI agents who are also programmers themselves. USL, what it really means is that we can settle correct executions on this common layer across Web3, Web2, all kinds of applications. Any computation that has nothing to hide, that wants to prove that it happened correctly, can settle on the USL. Web2 or Web3. Everything, everybody, any computation can settle. AI agents can settle their inferences. And UCP means that we no longer have to wait seconds for finality. It will happen at the speed of light. I don't need to tell you how important that is and what opportunities this brings. Basically, any developer in any language can now participate in the Web3 space. We no longer have to go with only 20, 30,000 programmers like today. We can very quickly extend to 20, 30 million developers, not to mention all the AI prompt engineers. Programs in the future will be written by AI agents, not by humans. And all those will participate as well in the Web3. All right, so enough talk about universality in general. Let's now go deeper and try to understand why we need universality. Actually, instead of why, actually that's not the right question, why universality. The right question is, why don't we have it yet? Because you want universality. I hope I convinced you that we want all that universality to eliminate fragmentation or reduce fragmentation. Why we don't have it? Well, programming languages come into the picture here. This slide shows the state of the art in the programming language field. It's a lot of pain, what this slide shows. Basically, every single programming language combined with any single tool is an arrow in this picture, and that means a whole complex system by itself. For example, C and compilers. We have GCC, ICC, Clang, tens of years of effort, hundreds of many years of effort. Or Java interpreters, or EVM interpreters like Get, Rest. So all of these tools need to be developed and need to be maintained. You cannot just add a language to an ecosystem. You need to bring all the tools so developers can develop actual programs properly using the language. So maintenance is a hell, training developers is hard, and tools are always behind 2 or 3 versions of the actual language. So bringing a new language to a blockchain, or anything for that matter, is a big deal. And this is what we believe is a major barrier, a major obstacle that we have to avoid. Well, how can we do that? How can we avoid that? And this is what we believe is the key to avoid all this fragmentation of programming languages and eliminate the barriers brought by programming languages. This is not a new idea. I proposed the K framework back in 2003 when I started my career as a professor at the University of Illinois. And I built it with my research lab, my students. Then several companies adopted it, several other universities adopted it to teach programming languages. But this is the idea. Actually, let me tell you what I don't think is the right way to go. Picking one particular language, no matter how beautiful the language is, and no matter whether that language is high level or low level, LLVM, any language that you think this is the best language ever. And by the way, I mentioned LLVM because it was invented in our department at the University of Illinois, so I can mention it. So pick LLVM, no matter how beautiful the language is, it will never be the ultimate programming language. Right? So if you compile translate any other programming language to that one language, you'll suffer from the same problems like before. You'll have compilers that you have to keep updating, you'll have each tool that needs to be updated, and you'll have errors, and so on and so forth. So we believe that the solution is to actually do the exact opposite, which is what I proposed back in 2003. So instead of translating everything to one language and call it the ultimate language, instead of that, what we do, we define everything mathematically. Every single programming language is a mathematical theory called a formal semantics. Let me ask you a question here. How many of you here knew, and be honest, that in order to talk about correctness, somebody gives you a program and says this program is correct. So in order to even talk about correctness, you need a formal semantics of the programming language. How many people here knew that? Nobody? Okay, you see? So that's what happens. People talk about correctness all the time, but in order to have correctness, you need a formal semantic, which is a mathematical definition of the programming language. Once you have that, a universal language framework, like the K framework, will generate for you all the tools that you need from that mathematical definition, including an interpreter. Okay? So you don't have to implement an interpreter by hand. You don't have to implement a compiler by hand. You don't have to implement a program verifier by hand anymore. All right? All of them are generated from the actual mathematical definition of the language, and they are correct by construction. What that means is that everything they do, including the interpreter, which executes a program, everything they do is done using a mathematical proof under the hood. Okay, so you can take that mathematical proof and check it, and now you know with absolute certainty. Forget zero-knowledge proofs. There's not absolute certainty. But this is absolute certainty that the execution happened correctly, because a mathematical proof was constructed, and that mathematical proof was checked. All right? So that's the magic of a universal language framework. Any programming language in the framework is a mathematical ground truth, a set of axioms, and now everything that you do in terms of execution, verification, everything you do with that programming language becomes a rigorous mathematical proof that can be checked. So this is the key that allows us to get universality, because there is nothing specific to any particular programming language here. And you may say that, yeah, that's great, but it must be horrible to define a language mathematically. And I can tell you that no, far from it. It is actually easier. And you don't have to trust my word. Just look at this slide. It is easier to define a formal semantics of a programming language than to implement an interpreter for that programming language in some ad hoc programming language. What you see here is a complete language definition of a simple programming language, but what is important is that it's complete. On the left, you have the syntax. You can see the if-then-else statement, for example, here in the middle. To the right, you have the semantics. All right, the if-then-else, notice that it's strict in the first argument. You have to write strict in the first argument. That means that it evaluates the first argument. And then in the right side, where you have the semantics, the actual axioms defining the language, we have two different rules. One when the first argument is 0, one when it is not 0. Exactly what you would expect. I claim that this is much easier to read than an actual interpreter for the language. But the beauty of this is that this is very rigorous, mathematically very rigorous. All right, so now what is pi squared? Pi squared comes from proof of proof, specifically from zero-knowledge proof of mathematical proof. Okay, remember that in K, when you execute any program in any programming language, you get a mathematical proof under the hood, right? Wonderful. The problem is that that mathematical proof can be big, and it is big, so big that you may not even be able to store it. So the secret is to actually discard it as it is generated, you check it, and you generate a zero-knowledge proof of its existence. And this is where the name pi squared comes from. Zero-knowledge proof of mathematical proof. All right, this slide shows the big picture, which we call Verifiable Computing 2.0. Why? Because this is verifiable computing as we know it, but universal. It works with all programming languages. It is correct by construction. No ZKVM to be formally verified. All right, this is how it works. Let's start with the output. At the output, we get a zero-knowledge proof, same like in any other ZK circuit. At the beginning, you get as input a program and an execution environment. Don't look at this yet, which is exactly what you get in any ZKVM, which is specialized to this particular programming language in which the program is written. What is different here is that the programming language itself is an input. All right, and then K does its magic and generates a mathematical proof from the execution of the program. Right? So now I don't have to trust any of these complicated stuff because I verified the mathematical proof. Once I verify the mathematical proof, I know that the execution was correct with absolute certainty. How can we do that? Well, we can do it using ZK technology. So now we completely separated concerns, computation from cryptography. Computation is verified with the best that we know after more than 50 years of research in programming language semantics and formal semantics in general, now we are done with this part, and now we can focus on just one aspect. Let's generate a ZK proof for mathematical proofs. This builds on everything we've learned in probably in the oldest field of computer science, programming languages. And it is not only universal, that it works with all programming languages, but it is correct by construction. There is nothing to formally verify here. And formal verification is my field. That's what I've done all my career. Now, finally, we don't need it. All right, and this is my last slide. Let me tell you what the current status is. We are a new company. We started 1 year ago, exactly 1 year ago, at ETHDenver 24. And this is what we really wanted to do back then. First of all, no matter how many times I said correctness is critical, in the end, everything boiled down to performance. Everybody asked me, yeah, but this is going to be slow. Great, it will be correct, everything correct by construction, but it will going to be slow. Not anymore. So we had to improve the performance of K by 10x, to make it 10x faster, in order to be convincing. And now it is actually 15 times faster than it used to be after 1 year of effort. Now it's 1.58 faster than GET. Okay? Please, if there is one thing to go home with, this is the most important thing. You execute a program generating a mathematical proof using a prover, and you get a proof of correctness for the execution of the program using the most rigorous known framework for correctness that we humans know. And that happens faster than an ad hoc manually written interpreter, which is the most used client in blockchain. Okay, so this is fascinating, for me at least. It's the first time that happened. So formal semantics, whoever tells you that formal semantics is great but it's slow, tell them not anymore and send them to this. By the way, all these papers confirm and explain how it happens. So this paper explains all the engineering that has been put into this, how to make it really, really fast. The second thing we wanted to demonstrate was that proof of proof makes sense as a concept, that we can indeed generate zero-knowledge proofs of mathematical proofs. And we plan to do it with just one ZK VM with risk 0. But what happened was that once we started getting results, we were approached by other friends, different other ZK with other ZK VMs, and before we knew it, we ended up putting together a benchmark, which now is the largest benchmark for ZK VMs that we are aware of. Has almost 10,000 programs, more than 1,200 programs, but multiplied by 7, because now we run them with 7 different ZK VMs. And yeah, so it's all open source. If you have a ZK VM, please try it and add the 8 or the 9th or more. So the bottom line is that now, because of what I showed you previously on the previous slide, we can bring all programming languages to all ZK VMs. Okay? You no longer have a ZK VM for RISC-V or for EVM. No, now you have a ZK VM for all programming languages without any compiler to your language. And finally, we wanted to show that we can indeed settle on the USL claims corresponding to blocks on Ethereum, and we've done a lot more, actually. We managed to integrate with Wormhole. So USL now provides an alternative to the Guardians on Wormhole, which we all know they are a big pain. They run full nodes on all the networks. So now you can settle everything they do on the USL, actually. And one other thing that happened last year is that ULM, the blockchain architecture that supports all programming languages, plug-and-play or language, now is actually alive. It's not a blockchain, it's still in our lab, but it's a proof of concept showing that, yes, you can plug and play your programming languages, and then write smart contracts in them, and then you have interoperable programming languages. So interoperable programming languages, interchain applications, everything going through mathematics and mathematical axioms, and 12 mathematical proof rules that can prove anything about any theorem about any mathematical theory. And with this, I will pass it to Ovidiu, who will talk about this blockchain ULM and will demonstrate it as well live.
Thank you, Grigory. GM everyone. My name is Ovidiu, and I'm glad to talk to you about ULM, which is something I've been working at with PySquared for the last few months, and we're very proud of what we achieved up until now. In the sense that you will see that in just a few minutes, we will be able to have one blockchain where you not just bring your own language, you bring your own languages. For now, we support Solidity, EVM, WASM, Rust, and also a special language that you've probably never heard about up until now, but you will. And we'll soon have also Move, Python, Go, JS, and so on. Now, let's talk some theory first. I'll be brief, I won't bore you, I promise. So, when it comes to formal semantics, it's basically a mathematical definition of all behaviors of all programs in that language. Meaning that if we have that mathematical definition of said programming languages, we can know how that programming language behaves in any VM, ISA, computational model, and so on. Moreover, we can have, using that definition, automatically generated language interpreters that are correct by construction and fast. Now, how do we get this and put it on a blockchain? We do this by having interpreters that should be able to modify the same blockchain state. That's one precondition. And we solve that by having all semantics implement the ULM interface. And second of all, we have smart contracts that need to interact with each other. I want to have my EVM contract calling your WASM contract without any issue. So that's why we have contract calls that take place through ABI encodings, meaning that all smart contract interactions are programming language agnostic. Meaning that if I have an EVM contract, I don't care that your contract is WASM, I can just call it like any other contract, and we'll prove that soon. Now, let's see how everything works for a minute. So first of all, we have a transaction that goes into the ULM, and that transaction is a contract call. That contract call sees what semantics it has to use in order to execute said call. Maybe it's EVM, maybe it's Rust, maybe it's Move, and so on. And using a ULM interface, reads and writes to the blockchain database. And that's how we do all those changes. The ULM interface basically abstractizes everything that's programming language specific when it comes to interaction with the blockchain database. And that's the beauty of it. Now, we went through enough talk. Let's see something hands-on. So with that being said, Musab, let's go through the Bring Your Own Language demo.
Let's see exactly how that works. First of all, we have a language registry which shows all the programming languages that are available on chain. As our chain is brand new, to say so, we only have EVM with a K beforehand. Why is this K important? This K is important because K is the open source semantics framework that we are using in order to define these programming languages and in order to then symbolically run those contracts that are written in those programming languages. We also have the language ID, which is going to be important, and I'll show you later why. And the hash, which has a role of checking, to say so, for authenticity reasons, in the sense that we can use this hash in order to see that this definition is actually the one we would expect to be, in order to be able to use this definition, because this is what this is, a formal definition of EVM in the K framework. And we can use this definition to get to this hash in order to check the authenticity of the code we run. Now, we already have EVM code that we can run. Let's use this EVM execution engine to add a new programming language. let's first of all add, Solidity. So we can add Solidity, and we're going to run Solidity directly on chain. Now, as we add Solidity, we simply confirm a transaction, and now as this transaction gets completed, it tells us what is saved on chain, and we can see that Solidity is available on chain. Now, we can run Solidity directly. So let's copy this ID because it's going to be useful and go and deploy this contract. Now, as I take the contract ID, I put it here and I can check the details of the programming language. We have added this so we are sure that we actually run an authentic language. And we can also add our contract. Let's deploy a USDC contract. So this code just gets hex encoded and then gets sent to the blockchain. Now you can see that it's recognized as a transaction for deploying a contract. And now we send this transaction to the chain, and we already have our first contract with its own address that's running directly in Solidity. Let's go and interact with it as well. We have this address, and obviously we need an ABI. All the programming languages use the same style of ABI encoding. So as long as we respect the usual EVM ABI, which we do by default, we can simply load the usual ABI, load the contract, and we can see it's USD coin, USDC. Let's quickly take our address and get our balance. Our balance is 0. Now let's mint some tokens. Let's mint pi squared tokens, and we're sending the transaction, and the transaction request is here. We confirm it, and now as the transaction will be completed, we will be able to also see a transaction receipt. This receipt contains all the usual things that you would have on an EVM chain, which shows that our execution engine is running as usual and as it should. Now let's read out our balance, and we see that we have 986 tokens. Now let's check this on the Block Explorer. We can see here that we have our own Solidity contract call, and we can see that it's in Solidity. We can see that we had a contract call, and basically this is as straightforward as it gets. One can see here the language ID, because this is important in the sense that this is how the nodes know, okay, what programming language is this in, and it knows what rules to apply to this, and this is the code you have seen before, hex encoded. Okay, we now have seen how Solidity works. Now let's go to the next language. Our next language that we can deploy is going to be Rust. Now, as we are adding Rust, let's confirm the transaction, and we can see we're saving the name, the URL, the ID, hash, and so on. We already have it, and we take the ID and we quickly deploy wrapped Bitcoin. We deploy the contract, and as the contract gets deployed, we're going to have the address. Exactly. And now put the API in, and here we have our token. Let's see our allowance. It's 0. Now let's add ourselves some allowance. Let's add just pi allowance now. Okay, it shows that it's a spending cap request. It's recognized as such a transaction, which is amazing. It's just like a usual EVM blockchain. Now, as the transaction is complete, we will be able to reread this and see that we have our tokens in our wallet. Now, we can check this on chain, and as we check this on chain, we can see it's Rust we can see the language ID here, all is good. Okay, we have this, we have Rust as well. Now let's also try and maybe deploy an actual EVM contract. Let's check that that works as well. So we're going to get the ID, we're going to paste it here, and deploy wrapped Ethereum. And by using this wrapped Ethereum, what we're going to do is that we are going to show that transfers of balance also work. Because in order to mint wrapped Ethereum, we need to actually send Ethereum. So we have 0 balance now. Now let's deposit some Ethereum. Let's deposit 0.1. We denominate it and we send it. Now, this transaction gets complete and I'll be able to see my depleted balance and so on. Obviously, as usual, the receipt. And now I can check the result and the balance is 0.1. Now, you can also see the balance of the contract is shown here. My balance has decreased. And also, I can go right here and see the contract, which was already picked up because of our activity as being wrapped Ethereum, and it has 0.1 ETH, and yes, that's as easy as it gets. Now let's go further, and we have already added Rust, directly Rust. Now let's add WASM. As we add WASM, it's going to be a transaction like all other transactions, and as it gets completed, now we have WASM on chain. Now we put the language ID here, we deploy our Doge contract, which you can see is already compiled to WASM. The transaction gets done, and as the transaction is done, we go here and let's see it do its magic. Now I'm going to copy the address and mint some tokens real quick just to see that it works as well. Okay, as the transaction gets completed, let's read our balance again, and let's also check that this is WASM. And we have the language ID here, everything is working as expected. Now, last but not least, let's also add simple, which simple comes from simple imperative programming language, which is basically a programming language we have created as a toy to just play around and check that everything works as we would expect, just because we can. We wanted to bring our own flavor to this, to check, okay, how is it to actually create your own language and put it on chain? And so we have created simple to test things around, and it actually works. So simple, oh, let me get the ID from here. And simple, we deploy it real quick. And once this deployment is done, we also have the address, and the pi square token is right here, 0 balance. We mint again pi square tokens. Let's actually mint pi square tokens. We confirm it, and transaction is completed, and we have pi square tokens, and we can also see this transaction here. So this contract is here, hex encoded, everything works fine in our own programming language that we have created ourselves. Now, in the language registry, in probably just about under 10 minutes, we have deployed 4 programming languages, and now we have 5 programming languages on the same chain that are working seamlessly. This is the beauty of ULM and bring your own language.
Musav, you can I think you can stop this, and we can go back. We can go to the next demo, which is going to be the decentralized exchange demo. We're going to show how you can basically have a DEX that has multiple programming languages interacting between them. Basically, you can have a token that is created in one language and swap it for a token in another language. Now, let me explain the setup real quick. So we have our DEX contract, the router, the Pi Square token, the Rep Bitcoin token, DAI, USDC, and Doge. You can see real quick, our router, that is the DEX itself, is an EVM contract. Next, you can see the ID there as well, as it's EVM. And next token is Pi Square. You can see it's in simple. Next token is Rep Bitcoin in Rust. Next is DAI, it's EVM again. Next is USDC in Solidity. Next is Dogecoin in WASM. And what we're going to do is do a quick swap. We'll swap from USDC to Doge. What's relevant to know here is that here we don't show the programming languages because the interface does not care about the languages. You can see it's recognized as a spending cap request first. You have to approve the spending of tokens for the contract. And here it goes. Once the spending cap is processed, we will have also the transfer request. We approve that as well. And as that gets done, you are able to see that our balances have changed. And we can also check that on-chain. Now, this is my favorite part. If we look at the transaction on-chain, you can see that we have interacted with a KEVM contract, transferred 986 Solidity tokens, and received back 895 something Doge tokens that are in WASM. 3 programming languages interacting between each others in one single transaction or contract call. That is as amazing as it gets and as simple as it gets. It's not, I wouldn't even call it language agnostic. Like, the DEX, not just that it doesn't care about the language. The DEX doesn't even know they exist. It's language atheistic, if you want to call it like that. And you can see that it works as we say it does, in the sense that here's the code of the DEX, and here's the transfer. No programming language is specified. You can see that it's just where we send, what we send, and so on. And this is because we use, as we said, ABI encoding to basically make sure that all the inputs and outputs that are sent between programming languages are, let's say, normalized. So again, KVM, Solidity, WASM, one transaction working together without any issue. So this has been our multi-language swap demo. I think you can stop the recording, Musab, thank you. And that being said, I want to give the mic to E to continue with our next cool products.
Hello, everyone. My name is E, and I'm glad to be here. So first, I'd like to thank Ovidio for his very informative presentation on these universal language machines. So next, I will talk about our second component in our Universality Stack, which is the Universal Settlement Layer, and we call it USL. So if I want to give one sentence to describe what USL is, then it will be bring any off-chain data to on-chain in a verifiable way. So there are 2 keywords in this sentence, the data and the verifiable. And this corresponds to 2 important concepts in the USL, which are claims and proofs. Claims are anything provable, and the proofs are something that used to verify the correctness of the claims. So let me try to give you some examples of different claims and proofs. So first, we can use claims to capture the computations in any program languages and VMs. For example, we can use block transition claim that is interpreted as this tuple, the pre-state, the code you can think of as a list of transactions, and the post-state. So this tuple can capture the blockchain transition in any rollups. And we also can have this blockchain query claim that simply we call this view function on a certain state to get some results. And these claims can be verified through different mechanisms. They can either be verified through mathematical proofs, or they can be verified through CK proofs in any approved CK VMs. And even they can also be verified through re-execution. Then we can also have the consensus proof, which basically states that a claim is included in a canonical blockchain. So the accompanying proof is usually a list of signatures from all the validators that approve this block. And we can also use the claims to capture those validated knowledge or information like oracles or identity. And we can prove them through digital signatures or certificates from zk-TLS. So now we have some basic concepts of claims and proofs. The USL is just a decentralized network of incentivized verifiers. And those verifiers receives claims and proofs from users or applications and verifies them. So there's one important property of USL that I want to highlight. First, we require those claims to be self-contained, meaning that they can be verified independently. And then all the verified claims actually form a set instead of list or sequence. This is very important because the order of the verification is not relevant anymore. And actually, they can be verified in parallel. This important property can enable us to achieve fast finality if we choose the underlying consensus protocol properly. That I will talk about it more in the implementation slide. So once the claims are validated, and then the claims are accumulated in this validated claim set, which is the state of the USL. And the USL also provides this so-called membership or inclusion proof for user to check whether a claim belongs to the USL state. So, and this membership proof are succinct and can be checked very efficiently. And all the applications or blockchains who wants to connect to the USL only needs to implement these simple verify membership functions. Okay, now so far I covered this universality of USL, which it incorporates various types of claims and proofs. And also, once the claims is verified on USL, it can be used everywhere. Next, I want to talk about this our implementation of the USL settlement layer. And we are collaborating with the pod team. Actually, we're implementing the USL on top of the pod. So first, what is pod? The pod is a layer 1 primitives that receives transactions as input and produce logs as output. But unlike the traditional blockchain or consensus protocol, so the pod doesn't provide a persistent total order on the transactions. In fact, the order of transactions are subject to change over time. And by accepting these features, it actually allows for making very performant systems. And the pod team has produced some theoretical results showing that pod is optimal in latency and throughput under some constraints. So as we said, we implement our universal settlement layer on top of pod. We implement the verification logic as a precompile and deploy it as some specific address on top of in the pod network. And submitting claims and proofs to the USL is equivalent to send this verified transaction to the pod network. So once this verified transaction is executed successfully, and it will be appended to the pod log. And we have this USL client to query the pod network for this log and the membership proof. This membership proof is just an aggregation of signatures of the validators from pod who approves these transactions. And then we can use these claims and membership proof anywhere in those dApps. So next part, I would like to introduce real use cases of our USL, where we use USL as a verification layer for the Wormhole's entity framework. So the Wormhole entity framework is a native token transfer framework that allows users to transfer tokens between chains by burning or locking tokens on the source chain and minting tokens on the destination chain. So under the hood, there's a message verification layer which verifies the messages between chains. And it also allows developers to introduce their own message verification layer, and they can configure which message verification protocol to use at runtime. So this is basically the basic workflow and how we use DCUS as a customized message verification layer. So first, user submit bridge transactions to interact with the entity manager. And this entity manager contract will burn the tokens on the source chain and construct an entity message that specifies the amount of token to be minted on the destination chain. So the message will be stored on the source chain, and we have this claim generator off-chain component to monitor the transactions on the source chain, especially those bridge transactions, and generate claims and proofs, which we will see in a second, and submit those claims and proofs to the USL. Once these proofs, claims are verified on the USL, the relayer component will query the USL for the validated claim and the membership proof and submit it to the destination chain. On the destination chain, it will first check the membership proof by running this verify membership function, and then they will parse the validated claim to extract useful information and performs the token minting. Now let's go to see the real demo. So I have prepared 2 demos, and let's play the first one. Okay, so this is the bridge demo where it allows users to transfer tokens from Sepolia to Arbitrum Sepolia network. So in this transfer tab, it is a very basic bridge interface. And on the upper right, there's a force button to allow user to mint some test tokens. In the history tab, it basically shows the bridge transaction histories, and each entry contains information like the source and destination transaction hashes, the port transaction that verifies the claim and proof, and the claim itself. Now let's move back to the transfer tab and transfer some tokens. We already approved a limited amount of tokens, and now let's input some token to transfer. So okay, let's input 11 and then click the transfer button. So the standard is quite, the workflow is quite standard, and we approve the bridge transactions on the source chain. So now let's go to the history page and wait for the bridge transaction to be completed. As you can see, now the transaction on source chain is completed, and the port transaction is completed, and we just need to wait a little while for the destination chain to be a transaction to be completed. Okay, now the bridge is completed, and we can click each link to verify what is happening. So we first click the link on the source chain, and we can see that the amount of token is actually burned on the source chain. And then we click the transaction on the destination chain, and we can see the same amount of token are actually minted on the destination. As we said, so actually what happens under the hood is that our claim generator generates claim about the entity message and then submits to the USL for verification. Now let's see what the claim and proofs actually look like. So we can we can click the claim button, and it will show you the hex format. And we can click the code claim, and it will transform this hex format into human readable format. So in this assumption field, it shows the block header of the current block being queried. And then this action field shows the actual view function that we are called on this blockchain state. And the result is the entity manager that is being stored on the source chain. And we can further decode it to see the actual tokens, the amount of tokens to be minted on the destination chain. Now we can go to the proof tab to see the actual proofs that is being generated. They are actually the Merkle inclusion proofs for those storage keys that are being used to execute the view functions. Okay, great. And then once the claims are verified on the port, right, and then the relayer will submit this verified claim and proof to the destination chain, and we can check the transaction of the pod on this pod explorer. Finally, let's go back to the transfer page and verify that all the balances on the two chains are updated correctly. So this is the end of the first demo. Okay, so let's play the second demo, where I will show you a scenario where the claim generator stops working and the user can still complete the bridge transfer in a trustless way. So let's first stop the claim generator and then performs a normal bridge transfer. So we enter 21 tokens here and do the transfer. We click approve the transactions in the MetaMask, and we go to the history tab to see what actually happens. So now the transaction, a source transaction is completed, and we can see the amount of tokens is burned on the source chain. However, since the claim generator is not working, so no one will generate claims and proofs, and the whole bridge workflow gets stuck. Instead of waiting for the developers to fix the issues, the actual users can start the claim generator locally, because the bridge is actually by the claims and proofs. It doesn't care who actually generates the claims and proofs, as long as the claims can be verified by USL. So now let's do that. Let's start the claim generator in manual mode. Once in the manual mode, user needs to provide the transaction hash of the source chain and submit it to the claim generator. Let's copy it from the Explorer and give it to our local claim generator. Now we submit it to the local generator, and boom, you can see that it is job to generate proofs and claims and submit it to the pod, and everything goes well. Now we can check the destination chain transactions. And verifies that the actual amount of tokens are minted on the destination chain. I think that this concludes my demo. So, and I will hand over the presentation to Grigori for the UCP component.
All right, thank you. I hope you guys are as excited as we are about what happened here. Let me put things a bit back into perspective, okay? So we've seen multiple programming languages on the same blockchain. And we've seen programs written in these multiple programming languages where they interoperate on the same blockchain. Programs written in WASM, Rust, Solidity, and Simple. But Simple is a new language altogether. All of them on the same blockchain. Okay? It felt and looked like any blockchain using MetaMask to do transactions and everything. But what happened under the hood is critical, because everything was turned into a mathematical proof that was checked. Okay, so everything is mathematically correct. You don't have to worry about an incorrect implementation of an interpreter or compiler, right? Because everything was executed with the actual mathematical definition of the programming language. That has never happened before. Okay? We've seen zero-knowledge proofs where you have a way to generate a zero-knowledge certificate for an actual interpreter. Here, there is no interpreter, actually. There is just a mathematical proof that justifies an execution. The interpreter only helps generate the mathematical proof. Then we've also seen how we can implement bridges, so basically programs across different blockchains and different languages, also using the same infrastructure, where claims are settled once and for all at the speed of light, using a protocol called Universal Consensus Protocol, inspired and done in collaboration with the pod colleagues from the new pod company. We're also writing a paper together, so we cannot tell you a lot about the protocol right now. But What is important to know is that every single transaction generated a claim, which is a rigorously proved mathematical fact, which is verified by a decentralized network of verifiers who agree that that is indeed correct. And that happens only with a round trip of messages. So it's the maximum, it's the optimal possible consensus that you can get. What really happens here is that now we can use all programming languages to write Web3 applications. The programming language is not a barrier anymore. You no longer have to learn weird programming languages only to become a Web3 developer. You can use your favorite programming language. All you need is to plug and play it into the Web3 framework, and you've got it. That opens the Web3 space to millions. And if we include AI inferencers and AI prompts, hundreds of millions of users. And that's how it should be. With that, we thank you, and we are open for questions. We have 5-6 more minutes for questions in case anybody has any question.
What's the timeline to get to production or mainnet for the tech?
Oh, good question. So 6 months, let's make it simple. 6 months for testnet, 1 year for mainnet. And mainnet for us means the USL network that can settle claims in any languages and interconnected with several layer 1s and layer 2s as well.
Hi, my name is Nico. I'm super excited about what you guys are building. And something that I wanted to ask you, maybe you already sort of explained it, but I didn't get it, so sorry in advance. For the programming languages that you can implement, how different can they be in terms of, is it only syntax that, for example, you are building something in Solidity and then you're going to be able to build it in Rust? It's like Solidity with syntax on Rust, or how deep can you go with that?
The languages don't know anything about each other. There is obviously an API, a storage API they have to agree on. So they read and write using an API. So you have, when you define the semantics, you have to accept that API and define the semantics using that API.
Yeah, and that was my question about the API. The API is sort of like a generic form of what Solidity does. So in some level, you're still going to be we'll have to take care of some bugs that are in Solidity, but in Rust, because of the way that API is. Basically, the question is, how deep can you go with the language, and how different they can be between them before, so besides the syntax?
You have to stop at some moment where you say, this is my storage model, and every language has to agree on the storage model, how you access the storage model. For example, Move. Move has a slightly different storage model, more general than EVMs, but they can live together. We can go, that's very technical, it gets very technical. In some sense, that is what we call semantics engineering. So when you define a language, it's an engineering process, and you have to understand the semantics, you have to understand the build teams on which you build your semantics. Like numbers, you have to pick numbers, infinite numbers, finite size numbers, and so on. And similarly, you have to build to accept your domains on top of which you define computations above. And this is a moving target, even for us now, the storage model. We keep improving the storage model as we add new languages.
Thank you so much.
Any other questions?
Or you guys want to add more on that, on the storage model? No. All right. Thank you for the questions, and thank you for being here. And I hope you'll soon try USL and ULM. You can try them right now. Go to our website, and you'll find them there.